All right, so we're getting now to interesting things. Okay, so I gave you a broad overview before, high level, what are the issues that distributed systems people care about, and it was what? Mainly use lots of computers to do all kinds of great things, right? So let's see how that might actually be done. So in order to talk about particular solutions, we have to talk about this issue called architectures. And architectures is going to mean many different things in this lecture, right? It's going to be, to some extent, hardware architectures, but also organization of, at the logical level of distributed systems. So maybe the first question to ask is, why bother organize? Well, because if you don't organize, you're not going to be able to articulate a nice enough solution. You're not going to be understood by other people. You're going to reinvent the wheel over and over, all kinds of issues like this, right? Now, it's important to have ways to organize, talk about in a certain way material, but it's also important to recognize that you can break away from some of those issues and invent maybe your own terms, right? So I call this a selective wheel invention, right? So you want to reinvent the wheel in a very selective way, in a purposeful manner, to achieve a certain thing. You don't want to just randomly reinvent the wheel, right? It's good to know what other people did. It's good to know when you might want to break free yourself, okay? So let's foresee how already people in distributed systems have thought about this issue, architectures, okay? So I'm not going to go into how computers work, what do they do, what networking does. And almost anything involving distributed systems is going to obviously run on something that can run programs, computers, and it's going to have some sort of interconnectivity. Okay? Now, that might take the form of some sort of inside the machine connectivity or between machine connectivity. Networking people have worried about this for a long time, so we're just going to use networking, right? We're never going to get at an extremely low level when it comes to communication. We're going to assume that we do some sort of a TCP IP or maybe datagrams, UDP. But that's about all the level we actually care about. We don't care about the bits going on the wire in this class, okay? Or for that matter, in any class except a networking class, when we only care about the bits going on the wire for the most part. Okay, good. So when it comes to architectural styles, at least this textbook organizes them in the following way. These are the 4 primary architectural styles talked about: layered architecture, object-based architectures, data center architectures, and event-based architectures. Now, sometimes it's hard to say whether a particular system has one of these architectures or a blend between them or things of this sort. And take them as only some sort of high-level indication of how you might do things. Okay? Now, since we are talking about the actor model, and that's really what I wanted to use primarily in this class, I'm going to make lots of references to the actor model. And interestingly enough, actor model is going to fit perfectly well some of these architectures, but definitely be able to emulate all the other architectures. Right? Thinking in different ways is still helpful, even if you use, for example, a paradigm like the actor model that naturally fits one of this. And let's see which one it does fit. Okay? So layered architecture. So first, how many people took a networking class here? OK. So the layered architecture really comes from networking. I would even say the networking people are completely obsessed by layering. Okay? Any kind of network stack, it's about layers. Right? So they talk about 7 layers, and then they implement 5, and hope people notice 3. But in the end, these layers, right, are going to add various kind of functionality, but then why stack them? It makes the code, and it makes reasoning and the implementation a little bit easier to understand. So they figure out, and to some extent, they are going along with the initial implementation of, say, TCP/IP, right? They're reasoning that separating various functionality in these layers and then maybe optionally including the layers or not including the layers is going to make for a nicer implementation for the network stack. And virtually all network stacks have a layered architecture. Okay? The very bottom layer in a network stack is essentially Ethernet-like behavior, the bits that go on an Ethernet-like connection, and the highermost level might be something like the full-fledged TCP/IP behavior, right? So maybe the end checksum or things of this sort. Okay? So when it comes to protocol implementation, especially low-level protocol implementation, virtually the layer architecture dominates. But it's not particularly nice to reason about. Right? For the most part, when it comes to distributed systems, since distributed systems people mostly just use networking as a tool and say, oh yes, let's do TCP/IP. The kind of layered architecture is not particularly interesting. It's too constraining. So one particular constraining part in it is the fact that one layer can talk only with the layer right below. Right? So for example, in networking, the highermost level is going to be make some kind of a TCP/IP request, and then you go layer, 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 layer until, oops, smart board, okay. Until you essentially get to the bottommost layer, that's the request, and bits go on the wire, and then when something happened, everything gets propagated back. But you have to go through the intermediate layers. That's the problem in the layered architecture. Why not jump? So even network implementers have thought about better ways to do this. And by the way, some distributed systems people came up with interesting variants of the layered architecture to make it much higher performance. Right? And that was essentially by saying you have essentially a layered architecture, but you can optimize it and do jumps. Right? For example, if you could jump from layer 1 to layer n, which might be acceptable under certain circumstances, the network stack is going to run faster. Okay? But as it is, it's too constraining. Very important, though. It's important to know that something like this is used. Okay? Now, this is an object-based architectural style. Okay? You have various objects, and the objects somehow communicate with each other. This fits perfectly the object-oriented design. Right? Now, while it's nice, right, so this kind of arrows mean some sort of a method call. If you would put objects on different machines, then those arrows are still going to be some sort of method calls, but remote method calls, sometimes known under the name remote procedure calls. Right? It's a more generic, not necessarily a method, but a function in general. Right? Now, because of the object-oriented design taught in virtually all programming classes, or almost all programming classes, this feels like a very natural kind of model. Right? The trouble is, it's not quite clear who does what and when. Right? Namely, any notion of parallelism is not obvious at all. But this kind of a model would fit perfectly, let's say, an actor-based model, in which you replace objects with actors and method calls with some kind of a message exchange between actors. And then this starts to make a lot of sense. Right? But this is really not the intent of the object-based architecture. Right? Those objects quite often move in between themselves large part of the state and share things and whatnot. Part of the actor model is really try to keep to yourself the state you're managing, right? And use message exchanges to act on your own state and to send more messages to somebody else. Not necessarily true in the object model. Okay? Now, another one is the event-based architectural style. And you probably already say, hey, but actors have events. So actors are really some sort of a combination you can see now of some kind of an event-based architecture and an object-based architecture. In the event-based architecture, you have messages, but not necessarily any kind of actors. I want you to understand that the actor model, right, it's a separate idea. You can take part of it, just exchanging messages, and then you have this event-based architecture. You can take the overall object organization, and then you have an object-based architecture. You can combine both, and then you have some sort of an actor model. You might ask the question, why is the actor model not in the textbook? It's really not in the textbook. Well, it looks to me that this is the biggest blunder of the distributed systems community. They ignore this very nice, well-fitting actor model idea, right? Why? It's still not quite clear. Okay? Anyway, the event-based architectural style consists in some sort of a medium in which you're exchanging events. Now, what you do with the events and how you behave and how you manage those events, the architecture diagram doesn't care about that. The important thing is you have the ability to change these events. Interestingly, if you look at modern computer architectures, right, to a large extent they are actually event-exchanging architectures. For example, the way the cores talk to each other on an AMD processor is really this message passing that goes along. It's exactly this. They exchange these events. The events being somebody wrote in this location in the cache, update your cache. It's all that cache coherency protocol kind of thing. For the people that took some kind of an architecture class. How many people took an architecture class or are taking an architecture class? Even more interesting. But don't we have a core class that does this? Or maybe it's not core, but it's taught in the... OK. Anyway, it's potentially interesting to look at. Okay. The other one is, and this is really everywhere, okay? And I'm going to talk extensively about this in class, is this idea of a shared data space. And when you usually talk about data, I want you to understand this. You're talking about some sort of persistency, right? So data is supposed to outlive computers that exchange the data. So the trouble with all the other architectures we had before is things move around, but they will disappear if the computers basically get turned off. But the moment you start talking about persistency of the data is going to be pushed to some sort of a persistent medium, for example, a hard drive. So even if the computer has issues, goes down for any reason, when it wakes up, it still finds the data, right? That means the data now is really the core, and everything revolves around this data, right? It's as if we would use basically some kind of a written record, and if I want to do a transaction, right, I want to sell you something, for example, a house, we simply write some kind of a document that goes in the archive saying we've done that transaction. So if anything happens to us, somebody can go and look at the document. This is probably what revolutionized completely commerce and property ownership, right? You didn't have to defend all the time using some sort of a weapon what you owned. You could prove you owned something based on the written record. So that's kind of the ultimate in persistent storage, right? A lot of it goes hundreds of years back or more, right? Well, even going back a few milliseconds is tough in some of the distributed systems. So when you're talking about data, things change. You're suddenly worried about doing things to the data and not so much what all those computers that are alive or not do. Okay? So then everything is in terms of go and change this data and propagate the change to the data. Make sure everybody sees the same data. Okay? Right. Now, this is really I would say, the prevalent architectural style, especially when it comes to web-related anything. Right? I'm going to come back to this when I talk about classic architecture for web-based services, distributed system services. And data is always going to be there. Okay? By the way, this is why databases are a multi-billion-dollar industry, because everybody needs some sort of persistency for their data. So, okay, we're going to come back to this later. So it's mostly about data delivery. Of course, some machines have to deliver the data, but the important thing is the data is persistent. Okay. Now, I did mention the fact that there are a number of core obsessions for every area, and distributed systems has quite a lot of them, but one of the most important one is this centralized idea of centralized architecture. And not so much the centralized architecture, but the deep opposition to a centralized architecture. So distributed system research, for example, is mostly about removing the need for centralized anything, right? So whatever opposite of centralized you can find, you can potentially do some interesting research in distributed systems or build an interesting distributed system in the end, okay? Now, what exactly does centralized architecture mean? You have one or more clients and some sort of a server. The server is going to do all the heavy lifting, okay? Now, obviously, if the server goes down, there is no more service whatsoever, okay? Oh, it's easy to see how this would work because we are used to it. This is the classic client-server model. Okay? You have one or more clients, and the server is usually a big, powerful machine, and you ask the server to do things. The interesting question is what's on the other side? What could you have that's not a client-server model? Right? And this is the kind of questions that distributed systems try to ask and tries to find solutions for. Now, when it comes to any kind of system, it's important to think how the entire stack looks like. So, I mean, one of the biggest problems in general when it comes to software design is not having a complete view of how everything comes together, right? This is not only about various subjects in computer science, but this is a very important question is how the whole thing works, right? So an interesting question is to start quizzing people to say, okay, so we have an application on, let's say, a cell phone. Let's get down to the lowest bits, the lowest parts we get, and try to figure out how things actually work, right? Now, that kind of a question, I mean, first of all, it can become overwhelming, right? Most people have very weird ideas about how things work, right? So I try to explain, for example, to my wife how the internet works. Well, I had to give up after about 5 minutes because she said, okay, so I'm still going to keep my opinion that there is some sort of Holy Spirit that keeps everything together and just makes things work, and that's good enough for me, so that's it, right? But this is a legitimate question, how does it actually work, okay? Now, by the way, this is a very hard question to answer because it's easy to say what the mechanisms are, but it's not quite clear what all the parts do together. It's a very, very complex system. Okay. So the parts don't really describe the behavior of the entire system because it's not fully predictable. All right. So when it comes to the design of an application, there is some sort of a classic approach now. I mean, it kind of evolved over many decades, but it's now about there. And this is really what this slide is all about, right? So you have some sort of a user interface level, a processing level, and a data level. The data level, it's almost always there because you need to make things persistent one way or another. Ultimately, all computer systems are about exchanging some sort of information. Without that, it's kind of a sport without purpose. Right? I mean, who wants to create a distributed network just to measure how many messages we can send per second? It's fun for a little bit, but then what? Right? So when it comes to getting things done with computers, ultimately it's all about some sort of data exchange. Well, it could be movement in a massively multiplayer game, but it's still data. Okay? So it's data. I mean, it could be visual, it could be audio, it's still data. Okay? Good. So the classic architecture might look like this. Okay. So we have some sort of a user interface here. Then this level, the processing level, might have all kinds of fancy things. For example, some sort of a query generator. Then the information goes to whatever the database is, some sort of a data layer. And then data goes back. But raw data, especially coming from relational databases, it's really dry. I mean, it looks like some tables that are very boring. Now, of course, you could display tables, right? But that's really, really boring. So then what you might want to do is some sort of a nicer processing on top of the table. Maybe some ranking, some nice HTML generation, right? And then present the user in the user interface as kind of a nice web page, as opposed to just some numbers in a table. Okay? Now, you could see how this architecture might work, but let's say you want to actually implement this. The question is, where would you put various components? What runs where? Okay? And this, in fact, is a very legitimate question. Let me see where my other slide is. OK, so I want to talk a little bit about this slide. Okay? So in this kind of an architecture, right, you have the user interface, the application, and the database. Right? The processing layer is the application now. Right? The interesting question is, where do you separate the code that runs on, let's say, the true client, let's say my phone, or my desktop machine, or my laptop, or whatever you want, versus the code that runs on server, whatever server means. Right? Maybe the collection of machines that provide this virtual server. Okay? And now, this drawing suggests that basically you can have anything from a very, very shallow user interface. And by the way, this is what was happening in the times of very expensive computers. So if the computers are extremely expensive, and this happened in the 60s, right? Then essentially what you do is you produce lots of dumb terminals that can essentially just put letters on the screen, and they can take the keystrokes and send them to the server. This is the mainframe era, right? And then the server runs everything else, and then it switches between all kinds of various terminals. And the terminals are really dumb terminals, right? So for example, the terminals you have now, the terminal emulators you have now, let's say in Linux or some other Unix system, they are really, if you want, software emulation of a real physical device they had in the 60s, 70s. A terminal was only about $1,000, but the mainframe was $10 million. Hence, you had hundreds of terminals on top of the multi-million-dollar mainframe. So that means a really shallow user interface. But you could go to the other extreme. And by the way, yeah, so these guys drew the right picture, but so let me give you an extreme situation like this, right? The other extreme situation is a situation in which virtually almost anything runs on the client and very little runs on the server. By the way, the more on the right side you are, the more scalable the service is, right? Why? Especially if you have very powerful clients, and now even cell phones are very powerful clients. That means basically you can get away with very little on the server side. So then it's easy to serve hundreds, thousands, even millions of requests, right? Or any problems if you do very little, okay? So let me actually give you, well, let me give you an example, because nothing is better than examples. Okay, let me switch to a web browser. I didn't really intend to do this, but let me do that. So let's try. So let me describe as I go on the website. So this is basically visualization of Medicare data. In 2011, the federal government made available Medicare data in the form of a large table. Well, they made it available 3-4 months ago. A table with 163,000 rows, right? So you remember those boring tables that I mentioned, right? That's one of those boring tables. It tells you various hospitals that did various kind of procedures, how much they asked for Medicare and how much Medicare paid for every procedure. Interesting information, it's just that the table is boring. So what do? You pull it off in Excel, for example. But let's look at the web front end for this. Yeah, it will take me a few seconds. All right. So now something interesting happens. Did you see the loading data? That was what, about 2 seconds, right? And now some disclaimer, okay, because hey, right? Let me see if F11 works. So basically, this is a visualization on that data. You can click on a state. What did I pick? So I don't know, some sort of New Mexico, right? This is a disease. You can click on the disease. Things get computed in the browser. It's very nice. You can highlight something, right? Deselect this. So what you have is data processing at very, very high speeds, right? Sorts on the table, select states. Literally in 100 milliseconds, you get the answer for everything. So this makes that 163,000 row table fun to navigate, right? OK, now, interesting question. How is this done? How comes it works so fast? So how many of you ran a query on a database engine that over a table that has 163,000 tables, or did an Excel something? Right. So that was what, about 10 seconds, right, on most servers, depending on how you set things up. So how does it work so fast here? What's going on in here? Yes?
I think it downloaded all the data in JSON or some other format in the client.
So we're getting somewhere. So a suggestion here is those 2 seconds we had at the beginning, that was downloading all the data. Right? So remember the architecture we had on the board? The extreme version was everything except maybe the very lowest part of the database was in the client. It turns out that everything here is in the client except the raw table, right? Now, cleverly, the raw table was converted from a boring table format to directly JSON because JavaScript likes JSON. And essentially, every time you click anything in here on this website, it runs in the browser. It does query processing in the browser. So now you have query processing in JavaScript rather than send requests to the server, right? Now, this is good. Why? For 2 reasons. One of them, the server does nothing except serve that initial data, all right? It literally does nothing. It served the raw JavaScript code, the raw HTML. There's no changing. There is no HTML request. It doesn't matter what you click in here, right? Server has nothing to do. If you want to literally have 1 million people using this, as long as they can get it, the data gets cached on their machine. The data doesn't change because the feds don't publish more data, right? You don't even need to ask the server again. Data is cached on the client, right? So one way to achieve scalability is to push a lot of stuff in the client. And this is an extreme situation in which virtually everything is pushed in the client. Okay? But then, of course, you have to pull off lots of stunts in JavaScript. Okay? So why am I showing you this? Oops. 1, because it's possible. 2, because that's how you get scalability. Remember, the other core obsession in distributed systems is how do you scale things up? Well, you scale them up by asking the server to do as little as possible. Okay? So it's possible now to be even more than this, where there is almost no data. I'm sorry, there is almost no database. That's possible if you have mostly read-only data. Okay? All right. Good. Now, when it comes to this kind of message exchanges, you're going to see a lot of these diagrams, which you might have seen, for example, in a hardware class. These literally are diagrams, kind of information exchange diagrams that come from architecture designers in which you show some sort of a clock and then things go in a certain way, right? So when it comes to, we can borrow the same formalism. It's kind of nice, right? So when it comes to how things could work, right, if you have this simple architecture, the user interface could have some sort of a request operation to the application server who can have a request to the database server. At some point, the data is returned and the result is returned. Now, the interesting thing about this kind of an architecture is it doesn't really matter where you draw the line, what runs on the client computer, what runs on the server computer. It's still healthy to think about this architecture In particular, when you have to write that JavaScript code, so virtually the JavaScript code now does almost everything in the interface I showed you. When you're thinking about designing the JavaScript code, you essentially still want to have the same architecture, except now that any kind of message exchange is in fact some sort of a function call, right? So then selectively you can replace function calls by remote function calls or some sort of message exchange in one way or another, and you essentially can decide where to actually place various functionality. So I want you to understand that the architecture is dissociated, in fact, from the specific implementation, where things run, how they run, and what's actually happening. And this is one of the things you want to do when you discuss about any kind of software writing, but distributed systems in particular, right? Dissociating the ideas, the fact that you're going to do layering, that's a way to organize the data from specifically what is implemented where. All right. OK, now, I mentioned the fact that we have client-server architectures in which you have clients and servers. And by the way, that's how the web is powered, at least in principle, right? So when you want to read your mail, you go to gmail.com. That means you access some sort of a server. By the way, there is a lot of JavaScript magic happening in the Gmail application, right? Literally, Gmail drove the development of Chrome as a web browser. A lot of features and a lot of speed in Chrome comes from the need to do the kind of advanced email interface that Gmail has. Okay? And once Chrome got the speed, everybody else had pressure on them to increase the speed. And this is why we have good browsers now, right? Because of this application pressure. You want more advanced applications, you put more pressure on the mid layer, which is now the web browser, right? And then competition, progress, great browsers. Okay, I mentioned the fact that I've seen a 3D game running in a browser, right, Unreal Tournament. Right? Things are getting much better. All right, now, the peer-to-peer networks are the opposite, if you want, of centralized systems, in which there's really no more client and server. Everybody's both a client and a server at the same time, and it's some sort of a more global collaboration. Now, there are many reasons why you might want to do a peer-to-peer system, right? One of them is extreme resilience. For example, it's not enough to take down some of the servers to take down the entire service. And this might be important for many, many reasons. So how many people know about Napster? How many people know how Napster worked? So the key question is, one second, the key question we have to ask is, was Napster a client-server architecture, or was some more peer-to-peer decentralized thing? So, all right. Right, so Napster was the first service they wanted to be peer-to-peer. But in fact, part of it was client-server, okay? The question is which part? We're going to come back to Napster later, but which part was client-server? So you see, when it comes to accessing resources, we're going to see this later, you need at least two kinds of activities. One of them is to find the resource, who has the resource, and then to access it, right? Now, what Napster had is, who had the resource, who was the server that had the resource? They were really having millions of servers because every client was a server as well, okay, if it wanted to be. But what it had as a pure client-server architecture was the name lookup. The lookup between the name of a file, some sort of a directory structure, right? The directory structure was client-server. The content was peer-to-peer. Now, you see, if you take care of the directory structure, then you don't need much of an organization for where the content is, because you just get a random IP address, you go to that IP address, and you're done, and the TCP/IP protocol does its job. And it's very easy to implement the content access, just point-to-point connections. By the way, the network stack is designed so that every single computer can be both a client or a server at the same time. Namely, it can both open connections and listen for connections to be opened. And actually, both are needed to even run what you would normally think as being a normal client. Okay? Good. Now, why is this important? Because there is then a very clear way to take down the Napster service. What do? You shut down the name servers. It doesn't matter that you have millions of actual servers that happen to also be clients that have content. Now nobody knows where the content is, right? So if that's effectively what happened, I think, in 2001, right? The music industry was completely outraged. I mean, Napster was cool for a couple of years. They started to have hundreds of millions of users. Then they shut down the name servers. They only had about 14, by the way. And they were geographically distributed. This is a classic approach to do some sort of balancing, right? Load balancing to avoid having overwhelmed servers. If you have millions of people looking up in your name server, right? A single machine starts not to be so good, even if you're just saying this machine with this IP address has the file. Even that becomes overwhelming if you have millions of such requests flying at every moment. Okay? Good. So then what do? You design systems that have absolutely no centralization. Really, the goal there was not to do so because the Napster architecture didn't work. It worked perfectly, I would say. It was to do it because then it's virtually impossible to take it down. So if you could remove the need for a centralized name service, and you could have a true peer-to-peer, peer means everybody can act both as a client and a server, a true peer-to-peer system, then essentially even if you take millions of nodes off, the system supposedly is still running. So a core interesting question, we're going to see this later in the class, is how do you design these peer-to-peer systems that can survive this massive removal of nodes and still kind of tick? If you do that, then it's virtually impossible to shut down the system, right? And in fact, this is happening to a large extent with the torrents, right? You can shut one down, another one springs up. I mean, it's everywhere. Or pure peer-to-peer systems, okay? Now, when it comes to these peer-to-peer systems, you can ask a more structured question, is how should you go about designing them? Can you be systematic in a certain way? And this was really the darling research topic in distributed systems for a while. So people came up with a number of interesting solutions for this. One of them is this idea of a structured peer-to-peer network. So in a peer-to-peer network, you want to know about nodes, but not about all the nodes. You simply can't keep track of all the nodes in the system. If you have a million nodes in the system, accurately keeping track of a million nodes is essentially an impossible task. Now, I want you to understand that it's impossible not because you don't have enough memory to keep track of a million nodes. That's not a problem right now. It's simply you can't possibly know what even 10 guys for sure do, let alone a million guys do, right? So knowing which of the million are alive, because if you contact servers that are not alive, it's kind of tough, or distributing that information, right? When another node joins, if you really have a million nodes in and you have to tell this guy what all the million other guys do, it starts to be problematic, okay? So the structured peer-to-peer networks came up with a very systematic way to decide which are the nodes you should know about, which are the connections you should keep track of. And in particular, they were looking for just a logarithmic number of such connections. Right? Again, by the way, you can already see a little bit of big O notation obsession creeping in. Why logarithmic? This is a very legitimate question. Well, logarithms are kind of very nice, mostly because the theoreticians told us that logarithms are good, and anything that's not a logarithm is bad. But I mean, if you think about it, even square root might be fine, right? Square root of a million, it's 1,000. Well, 1,000 is not such a bad number of nodes to keep track of, I would say. Okay? But nevertheless, virtually all the structured peer-to-peer architectures like that logarithm, and they're going to keep track of only a logarithm number of such nodes. Okay? How they do that, we are going to go into many, many details later in the class, right? Is by coming with various tricks to be able to, in fact, compute which are the logarithm number of neighbors you should actually have, right? Almost all of them are based on an idea called the distributed hash table. Okay? And that forms some kind of a virtual ring, and jumping on this ring with steps of increasing size essentially gives you the logarithm number of steps. Okay? It can be proved that it has all kinds of nice properties as long as things don't change too fast, when it becomes very problematic to analyze in any way, shape, or form. Okay? Another approach is to say, you know what, let's view the space of documents as some sort of a multidimensional space, and let's cut it into pieces to determine who is responsible for every piece, and then to find a way to navigate this space, right? So in any such network, peer-to-peer or not peer-to-peer, the question is, how can you find the resource by name? Who actually has the resource by name, and then how can you grab the resource? Grabbing the resource, it's easy if you can do these point-to-point connections. So we're going to keep on talking about point-to-point connections versus some sort of a lookup, right? Point-to-point connections are by far the best approach right? Unless the network becomes overwhelming to get data. Torrents do something interesting there, right? Which is files get cached in multiple places to alleviate network strangulation, right? We're going to come back to this as well. This is also some sort of a distributed system strategy, right? So CAN is such a system in which some sort of a partitioning of a high-dimensional space is actually happening. And then things are easy for a while, right? For example, if a new node joins in, right? So you have this partitioning, a new node joins in and randomly picks a location in the space, and it picks this location. Then you have to split this location. You cut it in two. So the new node and the old node that own the entire location communicate and partition, say, the set of documents, right? And you partition the space. But then the trouble is when this guy dies, how do you put together such pieces? They're not nice rectangular anymore, so all kinds of complications potentially, right? So inevitably, what's going to happen is any such solutions are going to have some very nice properties under certain circumstances and some weird situations to deal with in other circumstances, okay? Now, one of your projects is going to be to simulate one of these things using actors. So it's going to be quite a lot of fun. All right. Now, something that you might have seen in the networking class. Whenever it comes to communication, you have to establish a so-called protocol, right? For example, it's easy to say an actor talks to another actor. But the question, of course, is what do they talk about? What's in that message? What one actor tells the other actor? Now, that's important. Why? Because if an actor tells something to another actor, then the actor that sent the message can assume about what the other guy at least will know after a while, right? And a lot of distributed systems are about who knows what. So what can you assume that the other party knows, right? Because if you can assume about what the other party knows, you can have a certain expectation for what would happen when you ask a certain question. And ultimately, it's about getting something from somewhere, right? So for example, in a structured peer-to-peer network, you can essentially figure out who should have a certain document because it's placed using certain rules. And then the protocol can reflect that, right? Now, at the opposite end, well, there are many opposite ends. But you can remove the structured peer-to-peer network. And that requires using hashes in a very clever way, one way or another. And you can have purely unstructured ones, in which it's truly ad hoc. I think Casa was like this, right? So Napster, big problem with the servers, and Casa came along in which you simply had a completely ad hoc association. All you had to know is another client that was part of the network, and from that guy you got information about what he knows, partial information about what he knows. So you can come up with higher level ideas, right? In particular, this idea that what you know about other peers in a peer-to-peer system is some sort of a partial view, right? So essentially then you say, hey, there is some kind of a global view in the system, is what the collection of all the peers do. But no specific peer is going to have a global view. Each of them are going to have only a partial view. So they know only about a subset of such nodes. When they exchange messages, they could exchange information about those partial views, right? So this is a particular strategy in which when a new node joins in, or when you want to talk about, let's change a little bit about what we know about in the system, and not really just going and getting those files, but trying to maintain some sort of information about connectivity, right? Then essentially what I can do is I can tell you what I know about my partial view, and you can combine it with your partial view. Now, what you do need is some mechanism to limit the amount of information you have to keep track of. So you can say, hey, I want to know about C peers. C is some sort of a constant. Okay, maybe it's logarithmic, maybe it's more than logarithmic, whatever it is. So essentially what I can do is say, hey, when I communicate with you, I'll pick randomly C over 2, half of the nodes I know about, and I'm going to send you a message and tell you about those nodes. And essentially what you could do is throw away half your information and keep the half that comes from me, and that will provide some kind of a dynamic component into the system that propagates the information. It's not quite clear why this is good, but potentially might be interesting. Right? Well, it turns out that this kind of protocols, these are randomized protocols, right, in which you randomly select some part of information and possibly even randomly select who you send the information to. These kind of protocols are extremely resilient. Now, it's very hard to understand intuitively why that's the case. And it's hard theoretically to prove why that's the case, but it can be proved theoretically. Right? We're going to come back to this later. These are so-called gossiping-like algorithms that have extremely good properties. If you truly pick a random node to exchange information with, then, for example, if you just want to say, one single message, right? Let's all agree that something happened. You can have this kind of virus-like dissemination that will run at exponential speed under a lot of circumstances. And we're going to come back to this when we talk about various networks, right? Exponential speed is very good in general, right? That means in a logarithmic number of steps, everybody knows about what happened. Now, this is a good logarithm, hopefully, as long as it doesn't have a large constant, okay? So strangely as it might seem, a lot of these distributed systems use purely randomized algorithms because they tend to have a very good average behavior, okay? I'm going to mention this later when we actually see specifics, but in fact, so how many of you took any class that had some kind of randomization in it? Sometimes randomized algorithms are taught a little bit as part of the algorithms class, right? There is even weirder stuff with pseudo-random, but that's a different story, okay? Well, you'll see some in this class. The important thing is a relatively small amount of information for each of the peers, together with that complicated theory, will guarantee that you have good properties in the global system, okay? And such an unstructured peer-to-peer protocol could be this one, right, with the push mode, pull mode. And this one actually stabilizes quite fast. If I share randomly with random neighbors, I share half my information, very fast you're going to know about very far away neighbors. And that's a good thing, because if you know about very far away neighbors, you're going to get that logarithmic behavior in terms of finding something very fast. Okay? Now, when everything else fails, if you want to find something, you can do something that's considered to be the worst of the worst, which is flood the network. You essentially start yelling, who knows where this file is? You tell all your neighbors tell other neighbors, other neighbors, other neighbors. They eventually guess to who has the file, right? That's one way to get information. Of course, to get that one piece of information with where is that file, you basically have to disrupt everybody. Everybody has to know about the fact that you are looking for a certain item. Now, of course, if the item is important, maybe that's warranted. It's like an Amber Alert, right? Everybody starts yelling. It can get worse than this, right? Because the yelling can propagate in waves and keep on bouncing off the network. If you have no way to cut down on those messages and make them die somehow, they can live for a very long time, right? For example, if you wouldn't remember that you've seen this message, you send the message to your neighbors to their neighbors, but you're part of the neighbors, so they get you back the message, and everybody keeps on just propagating these messages more and more and more and more and more, and then everybody doesn't do, I mean, all the messages in the system are just about this flooding that doesn't even have a way to die out, right? Now, you might say, hey, we must do something about it, but sometimes it's tricky to do something about it. So one particular solution, for example, I'm just throwing it out there, is some sort of a time to live, right? For any such message, you include a counter and you say, this message can be retransmitted only, let's say, 20 times. Every time the message gets sent again, you decrease the counter. The counter gets to 0, you stop sending a message. That will make the message die. It cannot propagate more than 20 rounds, right? Now, of course, the question is, why 20? What's special about 20? Or how many do you need? Right? So then you have a solution, but it's only a partial solution because it depends on magic parameters that you still have to figure out how you actually select. So if that number is large, you're guaranteed that everybody hears about it with very high probability, but then you do more disruption in the network. If the number is small, then maybe there are circumstances in which the right people don't hear about it, but at least you don't have so many messages going in the system. Right? It's very, very tricky business that needs to be treated possibly theoretically. Right? By the way, the theory on such systems gets extremely hard, even under idealized modeling conditions. Extremely hard. Right? Even partial success in doing some sort of a theory, and definitely distributed systems literature is not the realm of this. Right? Even partial success is it's kind of celebrated as a big breakthrough. Right? All right. So this is one such protocol. Right? Then you can write some interesting research papers in which you argue that even if you do an unstructured protocol, if you put an extra condition, it starts to look like a structured protocol. Right? I'm not going to go into all the details, but if you're a little bit picky about how you select that half information that you send to somebody else, and you have some sort of a measure for that, then you can actually see that from everybody with everybody connection that a very unstructured network might look like, it can get more and more structured and in the end look very structured. If you just have a particular preference in how you select the neighbors you want to retain over time. So the network can go from very intertwined to a lot more structured. just by being picky about what information you keep. So that's kind of an interesting result that says you don't really need to be structured from the beginning. All you need to do is add pickiness to unstructured, and it will form some sort of a structure. Now, if you think about this kind of a network, then it's not fantastic, because to get from one end to another, for example, this guy wants to find the file that's here, then you have to go through many, many hops to get there. So an interesting question would be, hey, I might want to have structured network, but some other links. How many such links would I need to be able to traverse the network fast? That's a theoretical question, and there are some interesting solutions to that. Okay, but all of them hard. I'm just going to mention these kind of results. We're not going to start proving anything about random networks in this class. Okay. All right. Now, I said peer-to-peer network. The peer in peer-to-peer means everybody is equal, right? But sometimes it's healthy to have some peers to be more equal than some other peers, and that's where the super peers come into play. Now, I want you to understand that a lot of these solutions came from evolution of particular systems, right? So I think Casa initially was simply a peer-to-peer system, but then they figured out that certain people have much better computers than other people and much better network connections, which is even more important. And they said, hey, why don't we give more work to the guys that have better network connections and better computers? And that's how super peers popped up. So the super peers simply can take a lot more of the load. And it depends on if you want to do some sort of a gradation between peers and super peers, or simply have two classes, peers and super peers. Now, the trick is the following: to still have enough super peers so you can't shut down the system. Original Napster system had essentially 14 super peers, which were the name servers, and everybody else was a normal peer. The super peers were just serving the names. You shut down, and the Napster company owned all of the 14. So all you need to do is get some sort of a court injunction. Since that company has to work in a legitimate way, you shut down the entire system. Now, if you have 1 million super peers and 100 million normal peers, good luck chasing down the million super peers, right? It's like flies. You kill one, more spring up, right? And this literally happens with a lot of these services. Okay? Now, these are interesting ideas that we might want to use even beyond just normal peer-to-peer systems, right? If you want to have these super resilient networks. For example, an interesting thing I didn't talk about, and it's interesting in itself, is this idea of sensor networks. So we keep on talking about computers, computers, computers. You have computers everywhere. Computers mostly consume data, and somebody has to produce the data somehow. How? Well, we can all say, yes, it comes from databases, and somebody bothered to put it there. But another way to say is something measures it, and those are the sensors. And that can be a very interesting kind of endeavor. You don't, a device, for example, by the way, this is coming. To some extent, it's already there, but it's possibly coming in a big way, because they're going to run out of gizmos to put in a cell phone. Soon your cell phone is going to be able to measure temperature, pressure, possibly even your heart rate when you hold it and stuff like that, right? And then suddenly you can ask questions like, what am I going to do with that information? That would be interesting. By the way, that could provide very interesting data for weather prediction. The problem with weather prediction now is you measure it in too few points. Right? You solve differential equations, and you simply don't have enough points to know exactly what's actually happening. Now, if you find any sort of application, for example, for so I mean, a cool thing I would like my phone to do is to tell me what the outside temperature is, because that helps me determine whether I'm justifying feeling cold or something is wrong with me that I'm feeling cold. This is why we have thermometers, really. Right? Because, I mean, otherwise we would feel. It's just kind of to calibrate our own senses to say, I would love to have a thermometer and a hygrometer on my cell phone to know it's humid outside or not humid outside. Now, the moment I have the convenience of having those sensors, you could gather that information. That's a sensor network. Okay? Or you could ask, could I deploy such sensor networks? For example, I do some kind of ocean-related research. I'm going to throw 1 million sensors, measure things with 1 million sensors, get in the information, and then, well, I can imagine things I could do with it. How many people saw this movie, but must be at least 15 years old? I think it was called Twister, with those tornado researchers. They had those little flying sensors, and the big highlight of the movie is when they all fly and they gather their data, right? That's a sensor network. Oh, that's exactly a sensor network. Now, interesting question. You have those little gizmos. They measure whatever they measure, and they send information. Now, that's the part that starts to become troublesome. What exactly does it mean, send information? Right? Who gets the information? How do you capture that information? How do you store it? How do you talk so fast with those sensors? Now, if it's just 10 of them, you can imagine a computer not having problems keeping up with it. But let's say a decent number to really get the shape of a tornado would be 100,000, right? How could you capture sensor information from 100,000 little devices? So that's really the realm of the sensor networks. It starts to be very problematic because you can't have each of those 100,000 talking to some sort of a server, right? You simply won't be able to keep up with so many things flying around. I mean, at least 100,000 TCP/IP connections of some sort. I mean, imagine writing a program that can keep track of 100,000 separate internet connections in a single machine. What are you going to do? Build a server farm to take it with you in the truck that has the sensor, right? So the idea is good. It's sound. You're going to have all kinds of small sensors to track how the tornado moves. But then the distributed systems component comes into play, and how do you get information from them? A particularly interesting idea, we're going to explore this, right, is you're going to have sensors talk to sensors and somehow propagate information, and then you have a lot less information to get from the system. Because ultimately what you want is some sort of knowledge that is not 100,000 measurements. Maybe a lot less would be good, right? So sensor networks are all about how do you cut down on the amount of communication. Not to mention that you need overly powerful antennas for all those 100,000 guys to talk long distance with the server. If they have peers, nodes, sensor nodes, close enough to them within a few meters, you can use much, much weaker signals and get stuff done, right? So that's potentially an interesting application of distributed systems ideas that we need to pursue. And that's a particular kind of, if you want, hardware architecture, okay? In those circumstances, you might, in fact, use some sort of super nodes and normal nodes, right? The super nodes, for example, could have more battery life. A big problem in sensor networks is battery life. Or you could even use the following kind of trick in which you switch roles, but at certain moments of time, certain sensor networks are super nodes, and then they switch roles because they drain their battery, right? By the way, the battery life is one of the biggest problems with any autonomous sensor networks. Okay? You can make them small, but then you have to put small batteries in them. That's the trouble. Okay, good. So lots of interesting ideas. Another one is this idea of edge servers, edge server systems. Okay? So when we think about we have clients and servers, even if you have the traditional architecture, right? The problem is the server can be on the other side of the planet, and then you have large latencies and whatnot. And a particular idea, this is what Akamai does, I threw it up in the air in the introduction, was to place servers much closer to where the client is, in particular at the ISP, right? Now, those kind of servers are called edge servers, right? Because they really live close to your actual connection to the internet. You don't then have to traverse the internet. And then what you have to make sure is that all the edge servers maintain consistent and maybe synchronized in some way information. So for example, you're serving the pages of CNN. And by the way, CNN is an Akamai client. Okay? So it's not a hypothetical scenario. So you're serving pages for CNN. Akamai's algorithms essentially make sure that when somebody at CNN publishes an article, they propagate fast enough to all the edge servers. And then the connection is very fast. All you do is you talk to the edge server. But the distributed system aspect of it, right, is how do you keep these edge servers in sync? That's even more problematic, for example, when you're actually doing transactions. You're Amazon, and you have multiple such edge servers so people can buy very fast, which means you sell more, right? You have two aspects today, and I want you to understand that it's important to realize there are two aspects. You can have two different solutions even though it looks like a single system. So one aspect when it comes to, let's say, e-commerce is what items are available and what's the description for the items. And the other aspect is the actual financial transaction, right? Now, how many of you bought an item from Amazon for Amazon later to send an email say, we apologize, but we don't actually have the item? I bought a keyboard, and this happened to me, and it's very annoying. Well, they suggested other sellers that might have it. But I already wasted a week, right? So you might ask, hey, Amazon has computers. Computers have storage. How comes Amazon didn't know that they don't have the keyboard? Well, because Amazon is cheating, and they are cheating with distributed system techniques in order to alleviate otherwise significant problems they would have. So in particular, they did not keep edge server synchronized, right? They said, hey, last night we had 10 keyboards. That's fine. We're going to tell the edge servers that we have 10 keyboards. And then all the 10 keyboards were bought without the information propagating to the edge servers. I jump on one of the edge servers. By the way, you don't even know if there is an edge server because you have to go through your ISP, right? And you think you go to Amazon.com, but you go to the edge server where your ISP sends you. That's all networking magic, right? Just routing and whatnot, right? That server said, oh, yeah, it sounds good. Give me the money. Actually did the financial transaction. Later, when they took the trouble to put together all of this information, they realized, oops, we don't actually have the item. No problem. We designed the system to be like this. So it's fault tolerant by mildly annoying the user, which is OK if you know what you're doing, right? So the lesson here is you really have to take tough choices, even if you're one of the big guys. You might think, hey, there are perfect solutions, and all of these big guys use perfect solutions. No, they're using perfect solutions that are designed in a very specific way, right? In this case, they know that if they don't do it too often, it's not a disaster. As long as they give me my money back. If they don't give me my money back, it's a disaster. But if they give me my money back, it's not such a big tragedy, right? So sometimes, and this is really the key to successful distributed systems, it's perfectly fine not to have perfect information or to have a little bit of lying going around in there, as long as it's done in a controlled way, right? And Amazon, it's a master at this. By the way, this is why they are so big and so successful. They just found the right compromises, this being one of them, okay? Instead of insisting on really knowing what you have in your inventory and then having a very big distributed systems problem, and potentially limiting how many people can do transactions at the same time, they say, hey, no, let's just do transactions and we'll figure out a solution out of it, right? Now, that's not true for the financial transaction. If I would do a financial transaction and sometimes it would fail, that would be a complete disaster. And by the way, there are strict regulations along these lines, right? You cannot play with money without giving very strict guarantees about what's happening with that money, right? So what Amazon can do, Visa and MasterCard cannot do. So for Visa and MasterCard, this is a tremendous problem, because when they say the credit card transaction went through, then it went through and it's a real transaction, right? At the level of a financial transaction, you can't cheat. But the important thing is you focus now the need to have a transaction everywhere to the need to have a transaction only on the very last step, just the money exchange. By the way, that's why MasterCard and Visa charge at least 2-point-something%, because they do this really fast, sophisticated distributed system that guarantees that you have real transactions, right? And by the way, this is why PayPal made a lot of money, because they figured out how to play their own game in the same space, okay? So to some extent, PayPal founders deserve the big wealth they got because they managed to build a really good distributed systems. It's all about distributed systems at this point. Okay, good. So let's read the story with these edge servers. Where you place them, how they communicate, what they do. This is why people use Akamai and not in-house ad hoc solutions. This is why people pay a lot of money to Akamai, because they already have figured out a lot of these things. Okay? Or this is why the big companies like Amazon design their own solution, because it's potentially expensive to go with somebody else's solution, because they themselves want to make a lot of money, right? Essentially what this means is that virtually anybody who's medium-sized or larger is interested in some sort of distributed system implementation, right? So it's a big market for people that understand distributed systems, because they all have to face these issues. At the minimum, how do you use certain software that already does some distributed systems, right? To know how to fix something, you have to understand how it works. Otherwise, it's basically just taking a hammer and knocking it on the side, right? It's not particularly good. Okay. And so this is a schematic of, for example, of torrent, BitTorrent, and some other torrent sites, right? In which you always go through some sort of a web interface. Even if you don't see it, by the way, most of the apps have a purely web-based interface. So they contact through a HTTP-like protocol, the backend server, even if they are actually implemented on your iPhone or whatnot, or on Android. Okay, that's very convenient because then you can unify apps on multiple platforms and web interfaces within the same kind of big umbrella protocol. Okay, so you somehow go to some web page with BitTorrents. It tells you where a .torrent file is. A .torrent file will tell you where fragments of a particular file are, right? As long as you make this resilient, as in multiple nodes know about torrent files, you solve that problem. It's not particularly centralized. And the torrent file will indicate, again, where fragments of the file are. And the important thing is, and this is one interesting thing, especially if you use encryption on top of this, nobody has the file. Every file is partitioned into multiple pieces, and you have to gather pieces from multiple places. It's easier to replicate then, to make sure that copies of every fragment are on multiple sites, right? And makes for an interesting distributed system. In fact, the torrents, if you think about them, are some sort of a file system. And they are, in fact, a distributed file system. This is one big topic we are going to study in this class, the distributed file systems. And one way or another, all the big companies have some version of this distributed file system, right? So for example, what powers a lot of the services that Google provides is GFS, the Google File System, which is a distributed file system that Google designed some 10 years back, right? Everything eventually goes to GFS for Google at least. HDFS for, let's say, Yahoo, some other distributed file systems. Okay. Now, to some extent, distributed file systems are the connection between the distributed systems and operating systems. Sometimes we call distributed systems distributed operating systems, even though for the last 10 years we kind of dropped the operating part, right? It's really distributed systems. When it comes to file systems, that's really the realm of operating systems. And by providing a distributed file system, you're getting close to what an operating system would do. Okay. Large discussion later to be done about this, but essentially BitTorrent is some sort of a distributed file system. Arguably, peer-to-peer networks are a distributed file system. So that begs the following interesting question. What's a file? So what are these files? So how many people did not use files ever? Right, that's what I thought. So what's really a file? So let's try to go deep, okay? Let's make it simple. I'm running an operating system, let's say Linux, and I create a file. What exactly is created where? What happens? I mean, it's some sort of bits somewhere, right? It has to be bits. We know that the hard drive stores bits. But they have to be organized somehow, right? It's all about organizing things. Well, it turns out that it's a little bit hard to say what a file is and where it is and how it is. How many of you know about in-memory file systems? So what's an in-memory file system? Right. So the files are written in main memory, so they're not even associated with the hard drives anymore, right? Why would you do this in-memory file systems? Yeah, but we have access to the memory. Why do I need files? So it's clear that faster access, but not clear that I need files. Why would I do files? But there is no persistence because it's an in-memory file system and it's never written on the disk. There is no persistence, literally. No, in-memory file systems don't usually have persistence. Right, so we're getting somewhere, okay? So the file is some sort of a universal abstraction that everybody likes to use, right? So that's the problem there. It has nothing to do necessarily with persistency because we throw away persistency for the in-memory version. It has to do with the abstraction. We are used to the abstraction, we like the abstraction, and all the programs use it, right? So this is why distributed file systems are suddenly extremely important because any program written to deal with files could use a distributed file system and be a distributed system, right? If you can distribute files, all you need is to read and write files, and you can have a distributed system. So this might sound weird, but one way for me to talk to you is I write a part of a file that's a distributed file. The distributed file system somehow gets the information to you. It's not actively pushed to you, but if you know where to look, you suddenly talk to me. You talk to me through a file, right? How many people know what a pipe is in an operating system? What's a pipe? Well, it really is a channel of communication that's made to look like a file. So it's again the file abstraction. So a pipe, it's a file, except that it never touches the hard drive and is really fast, but it's still a file. So it's all about files. So to a large extent, any modern operating system, it's about files, right? By the way, so this might sound strange, but you can even access the network through files. These are the sockets, especially name sockets, right? How does that work? Now it starts to be very, very weird. There's definitely no persistency whatsoever, because if nobody waits at the other end, first of all, nothing gets transmitted. Or if it waits and throws the information, nothing ever made it in a persistent way anyway. So what's that all about? Well, it's piggybacking on one abstraction, which is the file system. A completely different thing, this kind of communication. And it's, in fact, very convenient. Because in that way, so files allow you to make a certain resource available to other parties by just agreeing on some sort of a name. It literally can be used as a directory service. Right? So in that circumstance, the file, it's so-called a special file. The file just contains information about the fact that I'm really a socket, and this is the information about the socket, the IP address I'm listening to, who I'm talking to, and whatever else. Right? But then suddenly, all of that information that's about the socket has a name, and as far as the user is concerned, it looks like a file. You open the file, you send something on the file. Right? So distributed file systems can be regarded as some sort of view a connection as a file and put something at one end and it pops up at the other end in a very simple form, with persistency thrown in the middle to make sure we can dissociate in time the writing of the file and the reading of the file. Right? So you can write it and I come back later and read it. As long as I come after, it's fine if there is persistency. If you don't have persistency, you can still have the file abstraction, but we have to be there at the same time. I start writing, but I block until you start reading, and then I write, you read, and then we are done. We can still pretend it was a file. By the way, this is exactly what a pipe is all about. Right? The pipes in traditional operating systems require the reader and the writer to be there at the same time. Otherwise, one blocks until the other one shows up and does something. Right? If you think about persistency, that allows you to write now and somebody comes later to pick it up. So allows you more flexibility in what to do with that. So persistency might be there to just break this requirement to be there at the same time and not necessarily to keep the information forever. For example, temporary files with temporary results would work like this. Right? So that's kind of an interesting view of what files might or might not do. By the way, in most modern operating systems, every resource essentially is viewed through this kind of a file abstraction, including raw devices. Right? For example, even when it comes to a file, so how many of you know about file systems within a file? How many of you created a file system within a normal file? Well, probably all of you if you use some sort of virtualization with VMware. But for example, a particularly interesting approach to this would be this kind of encrypted file systems. So TrueCrypt, for example, is a very nice program, runs on all the platforms, that allows you to create an entire file system within a file. It's encrypted, so when you shut it down, it's basically sealed by a complex, presumably very hard to break encryption system. Then take that file, you put it on a USB stick, you transport it somewhere, you send it in an email, you pick it up at the other end, and you mount the file as a full file system. So what exactly does that mean? That means the operating system has the possibility to create this view of files, this abstraction of files, on top of any set of raw bits. So ultimately, there is not much of a distinction between a normal file that keeps bits and a bit interpretation that's a file system versus the original implementation of the file system on top of the raw bits that live on a medium. There's literally no difference in any decent operating system. And that immediately suggests that the raw device itself could be viewed as a file, and that's true in all modern operating systems, right? /dev/SDA, it's in fact a file that allows you access to the raw device, right? Now, why is this important? Well, this is important especially if you want to do tricks related to high performance. The file systems, because they are an abstraction, they add their own good and bad on top of it. They make things more convenient, but at the same time, they could rob you of some performance. For example, caching can happen that it's undesirable. Now, this sounds strange. Why would caching be undesirable? Because, and I'm not going to go into details, but I might later in the class, sometimes it's faster to write to some of the modern devices than to cache. We have, especially some of the SSD hard drives, can be extremely fast, right? So it's strange, but it might actually be faster to ask the raw device to write a piece of the memory than to have the processor copy that thing from one part of the memory to another part of the memory. And I've seen it happening. Okay? Under those circumstances, you definitely want to access the raw device. So knowing that you have this hierarchy of the files, and you have this idea of a virtual file system that simulates the abstraction at multiple levels of a file, right, might become important if you want to obtain such a performance. Also provides this ultimate convenience. All you have to worry about is a file-like interface, which is what? Open file, right? Read and write parts of the file. If you have random access to it, pipes don't, right? Close the file, maybe create file. But it's a very simple abstraction, right? It's very easy to write applications. You just open files, close files, right? Distributed file systems allow simple application writing on and to have a distributed system-like thing. Now, they might not be everything, and you see more and more systems now that use other paradigms, for example, like these remote procedure calls or some sort of a message exchange of some form. Okay? Oh, by the way, how could you implement message queues using distributed file systems? A very important question is how one abstraction can emulate other abstractions. Could you do this? Well, it's very simple. You just do file manipulation, right? If I want to send you a message, we designate a special file. That's a distributed file. So if I write it, the information is propagated, and I simply write to the file. I'm simply going to put the message at the end of the file, and you delete messages from the beginning of the file. Now, it's not particularly efficient, maybe, but it can easily be done with a distributed file system abstraction. OK, now, there are many distributed systems, some of them very popular, some of them esoteric, right? Almost all of them try to have a certain bend, a certain different approach, and cater to a different segment. Okay, so in this class, I'm not really going to talk about this is better than this one. I'm mostly going to look at details of particular systems. What is it that they wanted to cater to which specific scenario? What are some of the interesting features of that particular system? How does the technology work? In the hope that when you're faced with a particular problem to be solved, right, you can find your way to sort out through what kind of things you could try to do to carve your own solution. Now, something that the distributed systems community looked at for a very long time, and I would say this is a core human obsession, to find the ultimate solution, right? So an interesting question to ask in any endeavor you want is there such a thing as the best solution for this problem? End of story, no questions asked. Right? From a practical point of view, that would be fantastic, because if you find the best solution, you're done. You know, that's the best solution. We all use the best solution. Let's move on and do something else. Right? It's really equivalent in theoretical computer science to finding those matching lower bounds. You found them, you're done, at least from a big notation point of view. Okay? Well, it turns out that in distributed systems, there is definitely no best solution. It's all compromises. And that's true in almost everything. Right? A particular blend of compromises might lead to a different kind of solution. Right? A particular solution might be better under certain circumstances. For example, you might not need any fault tolerance whatsoever if your system is reliable. And I mentioned the fact that some systems are just extremely reliable. Right? Local networks are extremely reliable. You don't need to assume that you're going to have losses on the network. You simply don't. Right? For example, if you don't get a reply within 10 milliseconds, you know that the other guy is in big trouble in a local network. And those assumptions can actually be used to a great effect to have much faster systems. Right? If you have to send a message across the globe, right, to some other server, you're virtually guaranteed that something will happen. And most of the time it's masked by TCP/IP. This is why you don't notice it. Right? How many of you have done this? You try to go to a website, and it doesn't work. You press refresh, and it instantly goes. Right? 1 second. I mean, it was the same internet, right? You can't assume that the internet was very bad, and then half a second later, I press refresh is very good. So what happened there? Well, it's a very complex system. Nobody quite knows. Right? So sometimes, and this is an interesting approach, we're going to see this, right? Sometimes doing retries on the same activity might actually significantly improve your chance to get the thing done faster. But then you have to somehow deal with the fact that you already made another request. Now, that's not a problem if you ask for a refresh on a page, except if you try to do a financial transaction. When they actually put a nice banner there, please do not press the button twice, right? Until they figure out you can do that in JavaScript. So once the button is pressed, you simply change the state in JavaScript and you don't let people press it again. Except that sometimes the first click did not go through, right? 3 days later, people call the customer service and say, I clicked, you told me not to click again. Now what? Let me look, right? Now that's not good fault tolerance in the system, right? So now that sounds funny, but it's in fact one of the core issues. When you can reissue the same command again, and that potentially might make things go much faster, right? And when you cannot. By the way, that thing has a name. It's called, so particular activities that can be done multiple times with no harm done, they're called idempotent. Okay, for example, give me this page. It doesn't matter. I say 10 times, I just ignore the other ones, and I display the last one. When you're talking about financial transactions, they are almost never idempotent. Right? Now, maybe if you ask for what's the balance of my account, then it's fine. But if you say transfer $100,000, then it's definitely not fine if it happens multiple times. Right? Except when you can cheat. When could you cheat? It's exactly the Amazon approach. If you say, look, if you allow me every now and then to do a transaction but revert it within 24 hours, then I'll go ahead and do it. And if you have enough money in the bank account, I'll do 2 transfers of 100,000. Overnight, figure out that one is wrong and put the money back. Are you OK with that? Yes, good. Let's do that. For most people, that's not OK, right? Occasionally, your bank tells you that something happened to your bank account and is negative 100,000. People have experienced some of that stuff, right? Which essentially means what? That everybody's cheating one way or another. As long as you can resolve these conflicts, as long as you can reestablish this kind of a consistent state, you might be fine. So some sort of ideas pop up in here. Is this consistent state? What's consistent state? What does it mean to be consistent? We're going to bump into this later, right? You can say, for example, the one way to define transactions, we mentioned transactions last time, right? The begin transaction, do something, either abort or commit. And the requirement for a transaction to be a transaction is to leave the system in a consistent state. But you have a problem there. What's a consistent state? Right? What could be a consistent state? Well, why is this problematic? Because, so how many of you know about verification, hardware verification, or hardware in general? It's very hard to say if some device really does what it's supposed to do, right? Humans are not particularly good at designing things that really always work. It's always that uncertainty. Maybe sometimes it doesn't quite work, right? So when it works, we can call that some sort of a consistent state. It's something that we expected, we predicted. And anything that's out of what we predicted, we can call it inconsistent state. But we have a lot of problems even writing any single little program that for sure it's consistent. So then how can you talk about a distributed system that has so many other things going on to be actually consistent? Well, you can always try to give a definition with respect to something that has less of a freedom, right? So you say, your program is consistent, right, if it does exactly what a program that's running on one machine would do. Now, we don't know if the one machine program is consistent or not, but if I do what the one machine does, at least I didn't make it less consistent by doing it in a distributed fashion, right? So that's one specific trickery, even when you provide the right definition of what you're trying to achieve. Okay. Not to mention that you can actually prove negative results. Let's say you can never really achieve consistency in certain ways and so on. Okay, good. So global is one such distributed system, right? One of the interesting characteristics in global is that it can do redirects. Why would you do redirects? Well, an interesting idea is, and this is actually happening with the edge servers. You think you're accessing some server that's the main CNN server, but you're actually accessing a side server that's placed at your ISP, right? So these redirects are crucial for dealing with large loads. For example, when you're really going, let's say, to eBay, right? You'll go to eBay and try to do some kind of a transaction, right? If you don't use trickery, literally a single server would have to serve all the requests. And that's problematic at so many levels, okay? Especially when you have millions of people pounding on it. Now, what's the trick that large companies use? But by the way, they might use these tricks even in a geographically distributed way in which they have multiple such centers in multiple places. They use multiple servers to serve the request. I mean, when it comes to the HTML request, for example, for the web browser, right, most of the difficulty is putting together that HTML page that you get that contains some information from the backend database, but a lot of other fuzzy stuff in there. Okay. Some of it is, for example, pictures and other things that you can get in mostly read-only way. Right? Don't necessarily need to pull them from databases. So there is a lot of work to be done beyond just the actual database work, and you easily could do it on multiple machines. But then your problem is the following, is how can you give the illusion of a single entry point, but to have multiple machines that actually serve the request? And these redirects are crucial, right? So they're really one of the main mechanisms for which you can, in fact, provide a lot of the services we want to provide in distributed systems, some sort of fault tolerance. For example, one of the 1,000 front-end servers hiccups, so what? You just don't give it requests. By the way, when you're doing that, it doesn't load, and then you press reload, and it goes through. It could be that you got sent to one of these servers that, for some reason, was stuck. But when you do a refresh, you're sent to another server. So there's some sort of component that can actually do these redirects. Now, these redirects can happen in multiple ways. For example, with the actor model, what you could do is have a front actor that gets requests, but it doesn't do anything except delegate it to another actor. Now, of course, the question is, how would you implement this front actor? Now, you could use Scala and so on, and that will take you to a certain level. At some point, it becomes overwhelming. And literally, the thing to do would be to do it at an extremely low level. And this is where the networking people come in, right? So a lot of these redirects can actually be done deep in the networking stack, in the network protocol, by the actual router. So these routers are extremely fast devices that can get hundreds of millions of packets now in and make hundreds of millions go in other directions. But they can do this magic with redirects also. How do you do that? Well, you simply replace some information in the packet with other information. So you want it to go to the main server that has a certain IP address. Well, this router can actually change the IP address and send it to one of the 1,000 other servers that can actually serve it, right? In fact, the TCP/IP protocol allows you to do this handover for a connection. You want to open a connection with this guy, but this guy hands you over to another guy, and then you establish the connection with the other guy, right? If this is not done at the very core of the network device, you have no chance to do large-scale load balancing. So that's an extreme version of this redirects. But these redirects can happen throughout the stack at a higher and higher and higher and higher level, including in JavaScript. So for example, when you install, say, a Linux distribution, right, you have to pick a mirror. An automatic mirror selection, it's in fact a form of a redirect, right? Because you just, I mean, literally this you can do. You go to the main website, and simply in JavaScript, you send a JSON object in which you say, here are 20 mirrors. And then JavaScript flips a coin and says, I go to this mirror. That's a redirect happening extremely high in the client, as opposed to happening deep in the network stack. But it's essentially the same mechanism, right? It's very good for open source projects that cannot buy those really tough routers that can do this kind of magic. They are very expensive, by the way. They can easily run you into millions of dollars, okay? I mean, they're really, really tough routers. By the way, this actually begs the following kind of interesting question. If you want to, let's say, attack one of the main websites, what would you attack? Now, it's hard to overwhelm 1,000 front-end servers. All of them can easily deal with 10,000 simultaneous connections, no problem, right? So you're talking about 10 million simultaneous connections. You really need 10. I mean, it's hard to keep them busy. You have to get all the computers on the planet to really pound on them to really make them sweat. Or you could just take down the front router. This is what happened in 2001. They figured out how to trick the front router, the one that was doing the load balancing, the tricks with the rewriting, the hijacking, right? If you take the main guy down, the whole thing is down. It doesn't matter that the backend servers are up. It's the same issue we discussed with Napster. You took the name servers down, you took the whole thing down. Even though the information was there was no way to get to it, right? So in fact, that main router at the entrance point is a centralized solution. This is the kind of thing that distributed systems don't like. Distributed systems people don't like. right? So interesting questions are, could you not have that router there and still do well, and, right? But still doing such a good job. I mean, maybe you can have a spare and you flip. Tricky stuff. By the way, these are important issues when it comes to databases as well. So you have databases that are now essentially cater to many, many, many clients. You still have to go and do some kind of transactions in the database, right? What happens if the main database goes down? For example, if that happens for Visa, it's a tragedy. I mean, people can't buy their snacks, right? It's cash only for the entire planet. That's not good. And it's possible that something like this would happen, right? When the whole network is down, right? Now, Google being down, everybody gets bored. The credit card machines being down, then that's a tragedy. At least for me, I don't have cash usually, so, right? All right. And so this is the kind of picture you can imagine, right? You could intercept at the request, you can intercept in the server, you can intercept at so many different levels. Now, why is that true? Because everything can be virtualized. Everybody can trick and present a certain view, but in fact do something very different, right? If we would really have every application talk directly on the wire with the raw device, and this was really the case about 20-something years ago, more, about 25, with the DOS operating system and things like that, then there is no cheating to be done, right? These abstractions allow cheating, which is good in this case. Okay? So a lot of what distributed systems would have to do, right, is to use such virtualization and to use such cheating and such this kind of rewrites to mask certain kinds of failures. Right? The server is down, well, I'll send you to another server. And you don't even know what was the server you wanted to talk to in the first place because they all look the same to you. Right? So in some services, if you look carefully at the URL, you might even see on which specific server something gets stored. Right? So you go to the main website, you go www.flickr.com, and then when you look at your pictures, maybe they are on one particular server, so it has a weird name. Okay. Some of them completely mask it from at the low level at the networking. Right? And by the way, when you access your Gmail account, the actual emails live on some server, not all on the same server, by the way, but they live on some server somewhere. So, I mean, some machine knows what your email content is. It's just all the magic that happens behind. That's this pure distributed systems magic. Distributed file systems or some other means will find where that file is, and it makes it back to you, and you don't know better. And you definitely don't care which of the million Google servers has your email. As long as more than one has your email, so it's actually fault tolerant. Right? Right. So one of the main things you would like to do in the context of distributed systems is to write this adaptive software. Adaptive is good, right? Because that means self-healing, self-monitoring, self-something. Right? That sounds fantastic because if it's let's say, healing, there is some damage to the system, it fixes itself, right? And then it's as good as new, and you keep on going, and it never shuts down. Right? I mentioned the fact that Ericsson did precisely this with Erlang, the first large-scale language to use actors, to in fact design extremely reliable telco systems. I mean, one way to do, so I mentioned this before, one way to do extremely reliable is to never do mistakes, which we have yet to see, or to repair any mistakes. You detect and repair mistakes, and then, right? If you can find the bad part, cut it off, and put another part in place, the user might not even notice anything more than a slight delay in providing the service. Okay? All right, so some of the approaches, and this, again, it's a way to be systematic about how you talk about this, but I mean, these are basically just fancy words ultimately, and you can do many variations on top of this, is separation of concerns, computational reflection, and component-based design. So the easiest one is component-based design. So why do we even do component-based design? Well, the trouble is, we as humans, machines are worse. We're not particularly good at keeping track of complicated things unless we break them into simpler things. This is what engineering is all about, right? Get an extremely complicated thing broken down into nuts and bolts and how you put them together and how you keep them together, how you build it and how you maintain it later, right? That immediately suggests some sort of components. So if we would be required all the time to express everything in terms of transistors, it would be a disaster. We would all just make those little sirens that go with slightly different sounds, right? But we build components. Some of them are full-fledged processor that just does all the magic, right? And because of that, we can accomplish a lot more things. Now, component design is to some extent wasteful because you're not using the hardware maybe at the highest potential, but at the same time allows you to do complicated things that otherwise you wouldn't be able to accomplish, right? For example, did you ever wonder how Intel is putting together those processors? So first of all, Intel has many thousands of engineers that design those components. They were doing so for many years. If you think they are redesigning everything from scratch every time, it's impossible. The complexity is just out of the scale. Plus, they buy designs from other companies. It's like buying libraries, right? Little company in Silicon Valley designs a very good floating point unit. Intel will license it. Why? It's cheaper, right? You cannot really go back to those transistors all the time, okay? And that, even at that level, is component-based. So libraries, for example, are one way to do component-based programming. You simply use prepackaged existing framework to get the job done. TCP/IP, it's an extreme example. Open connections send information. There is extremely complex behavior going on TCP, but it's a component, it's a block, just use it, right? So it's obvious why component-based design would actually help. And if you don't do this, you don't get anything accomplished, okay? Now, an interesting story, right? The importance of abstraction. So I found an interesting example when somebody got away with an extremely low-level abstraction. And I really admired the guy, right? So you normally, in what language are most games written? Anybody happens to know? It's C++ or C. I mean, it's kind of split now, okay? But it used to be pure C. But I found out about this game designer that was writing games in assembly as late as 2005. Okay? So this is a guy that started with assembly on the Z80 processor and really got into it, and then just went with assembly. So let me remember the names of the games he did. So he did the Railroad Tycoon and then the Roller Coaster Tycoon, and then whatever follow-ups on this. So he was the only programmer for the game, and he wrote everything in assembly, x86 assembly for the later games. Now, look, some people just have it. So they can work with crazy abstractions and get the work done. Most people can't, so they have to use higher-level components to get things done in higher-level languages, right? So, yeah. I mean, the exceptions maybe strengthen the rules in some of these circumstances. This is the only known example of an assembly, complex assembly-written game. And trust me, two people could not have written that game. It's only one mind can keep that craziness under control. Right? Two people cannot ever agree how to do things such a low level. OK, separation of concerns. This is going to be happening throughout this class. Is how can you deal with issues separately? Right? So for example, how can you separate the basic functionality from high-level functionality like redundancy, fault tolerance, and whatnot? Right? Because usually low-level functionality is more in the realm of the specifics, the application, and the high-level functionality potentially can be bundled up in a more uniform way. So then you might have more universal solutions for how do you make something fault tolerant. And to some extent, those high-level issues are harder to do, right? Now, computational reflection, this is somewhat of a weird one, because what computational reflection really means is the program can ask itself what behavior it has. I mean, what would the program ask? Well, because the program was written by the programmer, and it's usually not the same programmer throughout the time. And one way to diagnose yourself, or one way to know as a program what's going on, is to say, what am I doing, or how do I work, or what methods do I have? So this is something that happens in high-level languages. For example, this is a very, very neat way to program. For example, this is one reason I like JavaScript. You can get a random library of whoever wrote it, and in JavaScript say, hey, what methods do I have? I don't even care how that guy wrote his library. I'm just going to look at the methods using this reflection. What methods does it have? And I can guess what it is, especially if I do it in the console. But that can be done completely in the language. For example, in JavaScript, you can write a for loop to go over your content as an object. That essentially means that the content as an object is not fixed, as is, for example, the case in Java or C++, right? Oh, by the way, in Scala, it's also fixed because it's strongly typed language. But this reflection can come in handy in a big way, and especially can be useful if you have multiple versions of the same program. Because, for example, one way to make sure that you can work correctly is to say, do I have this functionality? If yes, I'm going to do something. If not, say, hey, this version is too old. Maybe you should upgrade. Especially when you get separate components that are not necessarily synchronized from a versioning point of view, right? So this computational reflection, it's a very high-level kind of feature that makes design of distributed systems a little bit easier. Okay, so it's a kind of a nice thing to have. You definitely don't have in C++. So how would you do this in C++? Can you, so maybe this is an interesting assignment. Write a C++ program that enumerates all the methods it has, an object has. In C++, you just know, because of the code, what methods you have, but you can't say, enumerate what methods I have, really. The new C++ standard has a little bit of reflection, but not significantly, right? In PHP, JavaScript, you can literally say, what methods do I have? Right? By the way, the original object-oriented language, which was the first object-oriented language? Anybody knows? OK, so I have C++, I have Fortran. Well, it turns out that none of the above. Yes? I'm sorry? Simula. Simula had some ideas in object-oriented, but the first pure object-oriented. I'm sorry? Oh, no way. Scala is so new. I mean, C++ is older. How many people heard about Smalltalk? Right. Smalltalk is the original object-oriented programming language and had reflection. The designers of Smalltalk believe that that's a crucial property of any object-oriented language. And then C++ came along and destroyed all of that, right? In Smalltalk, an object would say, what methods do I have? And then selectively call them or not call them. Smalltalk was designed to do graphic interfaces. And it's crucial for nice menu-based system and whatnot to have, in fact, some sort of an object-oriented programming interface. Makes it much, much, much easier. All the good interfaces like that have significant characteristic of object-oriented design, okay, with reflection. So why C++ designers knocked off reflection? Oh, because it kills performance, right? Forget about it. It kills performance. We're knocking it off, right? So to a large extent, C++ is not a true object-oriented language. It's a kind of object-oriented organized language, but not really an object-oriented language, not in the Smalltalk sense, okay? That doesn't make it bad. That just essentially says there are many flavors of everything, and you have to be careful how you call things and what exactly do they mean, right? So different kind of story. All right, now the last thing I want to mention is this idea of a feedback control model, because this is what will allow you to monitor yourself. Any feedback loop, this is a big issue, for example, in control theory. Any feedback loop consists in, you start with some initial configuration, and what you're trying to do is do some corrections. They have to be based on some sort of a loop in which you look at what you are doing. That means you measure it with some metric. You do some sort of analysis. You figure out how to adjust yourself, and you apply the adjustments, and you keep staying in that loop. For example, if you notice that a part of you doesn't quite work, and this is one great thing you can do with actors. You have actors that monitor part of the system. If they notice that something is hiccupy, one way to heal the system is you kill those components and create them anew. All right? Any of them ran in a weird state, if you can afford to do that and not overly disrupt the system, it's perfect. For example, if you have 1,000 servers, front-end servers, some of them will run amok for whatever reasons. Best way is to use these hardware devices that can simply cut the power of the machine and reboot it in a hardware way. And you start it again, 30 seconds later or whatever, it's like new, as opposed to running on some sort of a problem. So in principle, you could mask a lot of problems you might have. For example, you have a program that has memory leaks. You simply put an actor in front of it that watches it, and when the problem is too severe, you kill it, and it's like new. So you can mask any bad code with self-healing, which means you have to be a little bit careful how you use this self-healing. But in principle, it could be something that will make the system very robust. As long as you can do this, take it down, put it back up. And you can keep the system running while this is actually happening. This is one of the things Google does all the time. Okay, they monitor all the systems. They simply knock off the ones that don't work, and you don't even feel it because they mask the failure. Right? Actor model should make this a much easier exercise. All right, so this is it for this lecture. I'm going to go to my office and find the project and post the first project so you can start working on it. Okay, and we're going to have more fun Thursday and talk about distributed systems.